everyone. So in last video we ends with the topic chiral end or chiral molecule. So I am going to start from that only. So student, we discuss about the carbon, that is asymmetric carbon, and asymmetric carbon is responsible for the chiral molecule. So that was the example. Okay. So here it is the structure of propane 2-ol. Here we can see two similar groups are present to the central carbon, that is the methyl. That's why it is not considered as a chiral molecule, and you can see the structure C is similar, that is superimposable with A. Okay, and if you see this example, butane 2-ol, so one side it is methyl, other side ethyl, third side hydrogen, fourth side OH. And if you compare the structure of F with D, so there the structure is different, that the position of CH3 and C2H5 is exchanged, so we get the different structure. So student, we are getting two structure, one is D and other is F. Okay, in the case of chiral molecules. Okay, so the means we can simply say that here we are getting two structure from one condensed formula, and we covered the topic isomers, right, in class 11th. If structures are different and the formula is same, and it is said to be a kind of structural formula. Here it is related to optical isomerism. Here this D and F, this non-superimposable mirror images, are called enantiomers. So you can see the definition of enantiomers. The stereoisomers related to each other as non-superimposable mirror images are called enantiomers. Okay students, so this is the definition. The above part is the discussion of that butane 2-ol has 4 different groups attached to the tetrahedral carbon, right? That's why it is chiral. So here we are getting one more definition, what are enantiomers. Okay, and enantiomer possesses identical physical properties, namely melting point, boiling point, refractive index, etc. They only differ with respect to the rotation of plane polarized light. That means if one of the enantiomer is dextrorotatory, the other will be levorotatory, because their side is going to be changed. Okay, so what is enantiomers, what is the similarity, what is the different property, this we can see from this topic and this page. Okay, now next is based on a racemic mixture. Now what is racemic mixture? A mixture containing two enantiomers in equal proportions will have zero optical rotation, right? Mixture containing two enantiomers in equal proportions will have zero optical rotation, as the rotation due to one isomer will be cancelled by the rotation due to other isomers. So we already discussed in the properties of enantiomers, if one is dextro then another is levo. So when they are going to rotate, they cancel their rotation. Okay, clear? That's why it shows zero optical rotation. Such a mixture is known as racemic mixture or a racemic modification. And a racemic mixture is represented by prefixing DL or plus minus before the name. For example, plus minus butane 2-ol. And the process of conversion of enantiomers into a racemic mixture is known as racemization. Right? The process is called racemization, and the molecule which shows such kind of isomers is called racemic mixture or racemic modification. And here both the forms are there, so we represent with the help of DL or plus and minus. Now student, after this one, the topic is elimination reaction, second type of chemical reaction. So student, I already told you in the elimination reactions, saturated undergoes unsaturation, right? So you can see from this reaction, this compound, that the saturated compound changes to unsaturated. Student, in class 12, especially in this chapter, we discuss about a type of elimination reaction. Actually, depending upon the constituent based on the preference carbon, the elimination reaction is classified into alpha, beta and gamma type, right? It is the position of constituent. Okay students, now here especially in this elimination reaction, it is a type of beta elimination. Now why it is beta elimination? So you can see the halogen of alpha carbon is eliminated, as well as the hydrogen of beta carbon is eliminated. Now how can we give the position of preference according to alpha beta? The carbon to which the function group is directly connected is called alpha carbon. Next to that carbon is beta, and next one is gamma, and so on, like alpha, beta, gamma and delta. So here the first carbon from the right side where the X is attached is called alpha, and the next one is the beta carbon. Okay, and this elimination reaction is occur when this alkyl halide is treated with alcoholic solution of potassium hydroxide. Student, listen carefully. In this reaction, in the statement part, already the condition is given, right? But if you are going to change, instead of alcoholic, if it is going to be aqueous KOH, then the product will be different. So these topics are very much important during the conversion part. Okay, suppose you have to convert an alkyl halide, suppose ethyl chloride to ethene, so we can use this concept, just alcoholic KOH solution with potassium hydroxide. Okay, you can read it. There is an elimination of hydrogen atom from carbon and a halogen atom from the alpha carbon atom. As a result, an alkene is formed as a product. Since beta hydrogen atom is involved in elimination, it is often called beta elimination reaction. Now student, the other example based on elimination reaction is, suppose if we have 2 beta carbon, then what is the possibility of product? Which side we are going to give the preference? So student, if there is a position of, or there is a possibility of 2 beta carbon, then 2 products are formed, right? If you see that 2 bromopentane, with respect to bromine, that second carbon is alpha, and to left and right the carbons are beta carbons, right? So one product is formed, the elimination takes place to its left side, and the other in the case of right side, right? That means 2 product is going to formed. Okay, both are the alkenes, there is no any other type of compound is possible, only pen-2-ene and pen-1-ene, because the compound is 2 bromopentane. So this is the 2 compound, pen-2-ene and pen-1-ene. So these are the 2 product. Now student, how can we find out the major product and minor product? So for that is a very simple technique. You just see the structure of 2 bromopentane. To its left side the longest alkyl group is there, and to its right side the lowest alkyl part is there. That means 3 carbon chain is present in the left side and 1 carbon part is there in the right side. So the very simple concept is, how can we classify or how can we find the major product? The compound in which, or the side of double bond to which the larger group is present, larger alkyl group is present, that is the major product, and the side where the lowest carbon group or the alkyl group is there, that is called the minimum or major and minor product. Okay, students, and actually this is a rule, or this is a statement which is given by Sadjev, okay, in 1875. So according to this rule, in dehydrohalogenation reaction, the preferred product is that alkene which has the greater number of alkyl group attached to the doubly bonded carbon atoms. Thus 2-bromopentane gives pen-2-ene as the major product. I think this topic is clear. Okay, so very simple. Once again, when there is a 2 beta carbon with respect to alpha carbon, then 2 products will be formed, and the major product and minor product. Major product is that product which having the side to which the larger alkyl group is bonded. Okay, students. Now the next is the reaction with metals. So the first reaction of alkyl halide with magnesium metal in the presence of dry ether. After reaction it gives alkyl magnesium halide. Suppose it is alkyl bromide and it is react with magnesium in the presence of dry ether, it gives alkyl magnesium bromide. Student, the general reaction is Rx plus Mg in the presence of dry ether gives RMgX. This alkyl magnesium halide is called Grignard reagent, and the reagents are obtained by the reaction of haloalkanes with magnesium metal in dry ether. Student, this Grignard reagent is very much important raw material, we can say, which we are going to use in the preparation or the conversion of many organic compounds. Okay, so very simple. What is how many questions can be possible on this topic? So what is Grignard reagent, how Grignard reagent is formed, and write the reaction. Okay, so magnesium and dry ether is compulsory here. Now you can see when the Grignard reagents are highly reactive and react with any source of proton to give hydrocarbons. Even water, alcohols, amines are sufficiently acidic to convert them to corresponding hydrocarbons. So simply if you add water to Grignard reagent, it gives hydrocarbon, and MgOH is the intermediate. Student, in organic compound or in the organic reaction, the best part is what? That byproduct and balancing both are not so much important. If you write the main product, then it's okay. So most probably you try to keep the things that is the main product. What is the main product is going to form, that is very much important. Okay, now it is therefore necessary to avoid even traces of moisture from a Grignard reagent. On the other hand, this could be considered as one of the methods for converting halides to hydrocarbon. So what we are getting, if you think that if you start with alkyl halide, we can convert into alkane. First we convert into Grignard reagent by treating them with magnesium in dry ether, and then by hydrolysis it gives hydrocarbon. Clear, students? Now next reaction, that is the reaction of alkyl halide with sodium metal. Students, this is a kind of name reaction actually, but yes, this is the reaction based on reaction of alkyl halide with sodium. So when alkyl halide react with sodium in dry ether to give hydrocarbon containing double the number of carbon atom present in the halide, this reaction is known as Urge reaction, right? So the first condition is whatever the carbon is going to be present in alkyl halide, double this number is going to form as an alkane, right? Suppose you start with methyl chloride, so your product is ethane, right? If it is ethyl chloride, so your product is butane. So odd number of compound is not possible from this method or from this reaction. Student, this topic we also covered in class 11, right? Hydrocarbons chapter, we studied about the preparation of alkanes. So very simply we can say we use this method as a preparation part of alkane by using alkyl halide. Now after this reaction, there is a question. The topic we can say that is the reaction of haloarenes, but directly we can say this topic is directly going to be changed in the form of that why nucleophilic or why aryl halides are less reactive towards nucleophilic substitution reaction. So it's a complete format, right? That means especially this nucleophilic substitution reaction is important for alkyl halide. These aryl halides are less reactive. Let us discuss some points why this is going to be happen. Explain for that there are four regions. The first is the resonance effect. If you see this structure of chlorobenzene, due to resonance, there is a double bond formation between C and Cl, right? Clear? So very simple point. Due to resonance, CCl bond acquires a partial double bond character. As a result, the bond cleavage in haloarenes is difficult than haloalkanes because a double bond is shorter than a single bond, so it is difficult to break. That's why they are less reactive towards nucleophilic substitution reaction. So this is the first point, first reason. Due to resonance, it is less reactive. Now second is based on difference. Second point is difference in hybridization of carbon atom. Student, the carbon of alkyl halide is sp3 hybridized and the carbon of aryl halide is sp2 hybridized. So more or greater S character is present in sp2 hybridized, that means in aryl halide. Okay, and due to the more S character, the carbon is more electronegative and can hold the electron pair of CX bond more tightly than sp3 hybridized carbon in haloalkanes with less character. Thus the CCl bond length in haloalkanes is 177 picometer and in haloarenes is 169 picometer. Since it is difficult to break a shorter bond than a longer bond, therefore haloarenes are less reactive than haloalkanes towards nucleophilic substitution reaction. So very simple, due to hybridization, one having sp3 and other having sp2. If it is sp2 in aryl halide, so more S character. More S character, that means more electronegative. Due to more electronegative condition of carbon, it holds the electron pair more tightly, right? So it reduces its bond length also. So it is not easy to break a shorter bond than a longer bond. Now second is the third point is the instability of phenyl cation, and students this third and fourth point is not so much important to explain it, right? Okay, due to resonance, right? In case of haloarenes, the phenyl cations formed as a result of self ionization will not be stabilized by resonance and therefore SN1 mechanism is ruled out, right? Now fourth point is because of the possible repulsor. So these headings are simply important for this reason. You can get the direct statement from this heading only. Now what is the meaning of repulsion, possible repulsion? See student, haloarenes are electron rich as well as the nucleophiles are also electron rich. So in the case of same kind of reagent or attacking species, we can say there is an approach of repulsion, right? That's why this fourth point is applicable here. Possible repulsion between the electron rich nucleophile to electron rich arenes. So these are the 4 points on the basis of which we can say that haloarenes are less reactive towards nucleophilic substitution reaction than haloalkanes. So at last let's discuss some question which is based on chiral and achiral. The question is identify chiral and achiral molecules in each of the following pair of compound. Okay, so students, there are total 3 pairs. Okay, so students, for such kind of question I already told you during the explanation of chiral and achiral, you just find the central carbon and see the central carbon is asymmetric or symmetric. So from the first pair, if you see the first compound with central carbon, one side OH, other side H, third side CH3, fourth side Br. That means all these four constituents are different. So the first compound is chiral, and second one 2Br is there. So no any other confusion. Directly we can say yes, the second one is achiral. Similarly, in the second pair, if you consider, first you have to consider the central carbon. Central carbon is based on is the carbon to which the functional group is attached, that is called central carbon, right? So from central carbon, if you see, one side OH, other side H, third side CH3, and fourth side is a chain of 3 carbon, 1, 2 and 3, because it's a bond line or wedge and dash representation actually. Okay, clear students? So yes, here with central carbon all these sides are different. Okay, that means the carbon is asymmetric. Okay, so again here the first one is chiral, and if you see the second compound, okay students, so with central carbon, one is OH, other is H, but remaining two sides are equivalent. The length of the alkyl chains are same, 2 carbon chain. 2 carbon chain is there. I think you understood how it is 2. One is that point, other is the CH3, right? So again here two groups are same, that means the carbon is symmetrical carbon. We cannot consider asymmetric. So here also first compound is chiral, second is achiral. In third pair also you can follow the same concept. In third pair, the first compound, the central carbon is the carbon to which Br is attached. This is the again asymmetric carbon. You can count one side H, one side CH3, one side Br, and other side 2 carbon alkyl group. And in the second compound, Br is attached to the first carbon from right side, okay, and to that carbon 2H is connecting, right, CH2 2H. So again the second one is achiral and first one is chiral. Student, I hope you understood all these points. So today we covered enantiomer, racemic mixture, then elimination reaction, reaction with metals, Urge reaction, formation of Grignard reagent, right, and why haloarenes are less reactive towards nucleophilic substitution reaction. And we covered some example that how can we identify the chiral and achiral molecule by using the concept of symmetrical and asymmetrical carbon. Okay students, and in next video I will continue with the electrophilic substitution reaction, right? Thank you, and if you have any queries you can call me, right? Thank you.